Okay, so let's move on to the second speech of this fifth seminar of the BrIAS. And the second speaker is a Professor Barry Lennox, and is a professor of applied control at the University of Manchester, and is also an expert of nuclear decommissioning engineering. So we are touching another interesting aspect of sustainable robotics that Professor Barry Lennox will introduce us. So I invite you on the stage, and the floor is yours.
Hey, thank you. Yeah, I'm going to talk about, I suppose, there's two different aspects to the sustainability. One is that it's very emotive, but uh, nuclear power does seem to be becoming more gradually accepted that we do need it, and we need it in, I suppose, to work in partnership with other forms of energy provision. But we have in nuclear, there are very specific problems affecting robots. So often the robots can only be used once. They become contaminated. Can't take them out because they'll create problems. So that introduces sustainability problems, and also the speed at which some of these robots are being developed. That we're constantly just bringing along new robots, and we need to do something with the older ones. So I'll give you a kind of a very brief overview of nuclear. Some of you, everyone will have probably done it at school and will have forgotten, so it'll be dead quick. And then I'll try and explain some of the challenges in nuclear. There's some really fascinating challenges, whether or not you're supportive of nuclear or you don't like the idea of nuclear power, the nuclear problem still exists for us all, and so some of them are really quite interesting from a robotics perspective. And then I'll go through some of the solutions and deployments that we've done. Lots of videos so you can fall asleep after your break, and then I'll talk about one of our programs, which is called RACO, and I'll just explain a little bit about what that is, and if any of you are interested in getting involved in it, then that's fine. And I'll talk a little bit about some of the work we do in other environments outside of nuclear. My focus tends to be on nuclear. I thought, just in case you don't know, now we're now outside of Europe, and you're gradually pushing us out to the Atlantic. Um, this is where Manchester is, and I've listened to other people's talks, and they said, "Oh, I spent a year here, and then I spent a year there, and 2 years there." I've been 26 years here. Um, when I reached 25 years, they gave me 450 euros. I'm not sure if it was worth 25 years of my time. So I gradually used to collect lots of things through that time. Two things which I think are probably relevant. I was fascinated 2 weeks ago to see that VUB, lots of commercialization, spin out opportunities. I've been involved in two companies. They've taught me that I'm not very good at business and commercial things, but it's really difficult. But the people who started up these companies, Perceptive Engineering, and we've got a new one, Ice9 Robotics. Certainly, some of the people involved did very well out of those companies. So there are benefits. So this is let me just put the other stuff on. So just to give you a very quick reminder of radiation, we're interested in three different types mainly. Actually, we're interested in the fourth type, but alpha's great big blobs of things. It's protons and neutrons, and they're stopped very easily by pieces of paper. So you can work in an environment where there's lots of alpha radioactivity, provided you cover yourself up. The problem is that if you ingest any of that material, and that's where you often see people in suits going into an environment and cleaning it up. Beta is stopped by small sheets of aluminium and its electrons, and then you have gamma, and gamma causes lots of problems because it goes through materials, and it's not entirely stopped by aluminium here, and lead is reduced by them, and that causes a lot of problems. And it also causes problems to the electronics in any of the robots that we have. And very quickly, the reason we have a lot of these problems is that to create or to generate energy, what we're doing is we start with typically we start with uranium. You bombard it with neutrons, and then that splits the nucleus. And as you split the atom, then you get energy being released. But you also get this gamma radiation, so you create problems. You also get lots of different materials forming. So you've got different isotopes of uranium, they produce different materials, and they all have different half-lives and different things being emitted, different energy signatures. And so you get kind of lots of different elements being created. This shows, this was the, I've never seen photos. I don't know if photos were ever taken, but there's artists' impressions of, this was the first nuclear reactor. It was the Chicago pile. And it's a big graphite block. Graphite's there to slow down a neutron, so the neutrons will hit the uranium, and that causes a chain reaction and lots of energy and lots of neutrons. So there's lots of neutrons flying around in here. And when the neutrons hit things, they produce different materials. And some of those materials were going to cause problems with gamma radiation. So this also, if you read different articles, they tell you different things. But you'll be aware of control rods in nuclear reactors. When the control rods go into the reactor, they quickly absorb the neutrons and they will stop the reaction. What you had in here, you can see the rope, and you had somebody with an axe. And they would hit that rope with an axe, and the control rods would dive into the reactor and stop the reaction. And that was apparently where safety control rod Axeman came from in a scram system. I think there's some debate as to whether or not that's true. Now, this is the main, I suppose, problem area in the UK. This is the Sellafield site. This was started in the early 50s, and it was a response by the UK. What we wanted to do, what we needed to do, was to produce our own atomic weapons. And so to create the atomic weapons, we decided we were going to use plutonium in our weapons. So you have to produce plutonium. And this site here, it's about 1.5 kilometers square. It's a very big site, and it was developed primarily to create this plutonium so that we could generate these atomic weapons. There's also several nuclear reactors on the site, and the first nuclear reactor that actually contributed electricity to the national grid and the power network in the UK. And at the time, they said when they switched that reactor on, it was going to produce energy that was too cheap to meter, so they'd essentially just give us all the free energy. It sadly never happened. There's pretty much nothing going on this site now. All the systems have stopped, but what now needs to happen is you need to decommission this site. There are hundreds of thousands of tons of radioactive material. So you'll be aware of Chernobyl and Fukushima. They're reactors, and they have a limited amount of radioactive material within the reactors. This has substantially more than that, because it's over time, it's a lot of radioactive materials that have been transported here for storage. At times they weren't perhaps treated in the proper way, because there was such an urgency to create atomic weapons that they didn't always treat them and consider the long-term storage effects. So I'll show you some photos, but we've got facilities that are designed for 20 years. Well, they are still storing nuclear waste in those facilities some 50, 60 years later. And so there's a demand now to decommission this site and return it, whether or not it ever gets to a green field, but certainly to a non-radioactive facility. And this shows some of the facilities on the site. So on the left, that's an alpha decommissioning, people in air-fed suits, and they have, I'm not sure if this translates into French and Italian, but they have angle grinders, big mechanical equipment that cuts through the components in there. Now, just imagine if you're having to do that job. If you happen to cut your suit, then you're in an alpha environment, and if you ingest alpha, that's very, very damaging to your health. If you cut through your skin, then that's a huge problem. So although you can go into those facilities, it's not an area we really want to send people into. This shows glove boxes. So in these little holes, that's where you'd put your hands, and you'd be manipulating things inside there. So you might be moving materials around. These now need to be decommissioned, and the way you decommission them is you need to what's called size reduce them. So you cut these glove boxes up, and you would put them into a storage container. So it would require, there might be things inside those glove boxes where you can't see through, so you don't know what's in there. So the first thing you're going to do is put your hands in and have a rummage around, but it's rusted over the years, and so people have put their hands in and they've cut the hand, and then they've got large radiation doses. So we want to create robots that can go in and do this type of activity. This is a gamma facility, so depending on a particular facility, you might not be able to enter this. People may or may not be able to enter. So how do you cut up all these pipes without people going in? So there's a real need for robots, and some of these can be 40 meters tall. So we need great big robots that can cut, and we also need them flying around and doing lots of stuff. There's lots of aquatic areas. So on the left is a great big pond, 100 meters long. And you can just about see there's little skips in there, the containers. They have lots of radioactive material in. So thousands of tons of radioactive material. The water was there to provide a shield, so you can walk around. It's pretty hostile environment, but you can walk around the outside of that because the water is providing you with a shield between you and the material. One of the ponds, I don't think it is the one in the photo, they have sent divers into recently. Would you want to be a diver going into this? And this one in the middle, it's actually got silos. So inside this big building are 6 meter by 6 meter by, I think it's about 15 or 16 meters deep. Great big silos filled with water and then filled with waste. Quite a similar situation at Fukushima. So this is a schematic of one of the reactors at Fukushima. You had the reactor on here, and what happened in the reactor, there was a lack of cooling water, so the reactor heated up, the uranium fuel in here melted, and then it got so hot it melted through the steel casing of the reactor and then fell through, and you have this nuclear material at the base of the reactor. It's filled with water to different levels depending on which reactor it is. So you have water, and you've now got to try to go in and somehow extract this material. So it's a really difficult control challenge. Actually, one of the ways they're doing this is they have a 20-meter long robot arm that would sit over here, and it will go in and it will pick up some of the material. So think about if you have a 20-meter long arm and you're trying to pick up materials with it, and you'll get lots of vibrations. So it's a brilliant control problem. How do you reduce those vibrations and still be able to pick things up and move them out of the environment? So there's some really nice, for control engineers, robotics engineers, some nice challenges. Future nuclear applications. So that's kind of the historical, the legacy nuclear materials, and that's all there. It has to be treated. So whether or not you're pro-nuclear or against nuclear, the materials are still there, the facilities are still there, they need to be decommissioned. Future nuclear, well, in the UK, we're building large reactors like the one on the top left there, as well as small modular reactors, which are going to be smaller nuclear reactors. They will have environments where we don't want to send people, and we want to monitor and inspect and find out what's happening. So we need robots in the future. Fusion reactors, fusion is seen as one of, maybe in 20 years' time, we'll have operating nuclear fusion reactors. You have very similar problems. Inside this reactor, it gets very, very radioactive. So when the hydrogen atoms fuse together, you create neutrons are given off, and the neutrons will interact with materials around the reactor, and they will make radioactive materials. So fusion reactors are highly radioactive after operation. This is another challenge. So this shows you the scale. JET is an operating fusion reactor in, well, it's just been switched off now. It's in Oxfordshire in the UK. This is the Japanese fusion reactor. This is ITER, which is a European program, and that will lead on to demo. So these are just getting bigger and bigger. Inside these, you have these blankets, and the blanket inside the reactor is millions of degrees Kelvin. Outside the reactor, a point outside the reactor, you want it to be about 4 Kelvin. So that's a huge thermal difference. And you have these blankets, which help provide some thermal protection, and they also absorb neutrons. These need to be maintained. They need to be lifted in and out of the vessel. So you need enormous robot arms to lift them in and out. Again, you're lifting very heavy things and they will vibrate. The tolerances are maybe a centimetre either side. So you have really complicated control systems to be able to lift these things in and out of reactors. So lots of robotic challenges. So these, I'll go through some of the robots we've developed and show you where we've deployed them. It might give you some of our ideas of how you can make better robots. What we're trying to do really is to demonstrate to the nuclear industry that robots are available and they can provide solutions to some of their problems. So I'll go through each of these in the following slides, but you'll recognize some of the robots. Where we can, we use off-the-shelf robots. So this one here is a ClearPath Jackal, which some of you might have used. Some of them, like this one, we've completely designed ourselves. This is an off-the-shelf drone. This is one that we've designed ourselves. So where we can, we use off-the-shelf. Where we have to, we build our own. A lot of the time, we have to build our own because of restrictions with access. So this is one of the deployments that we've had. I think some people think there's lots of robots being deployed in the nuclear industry, and actually there's very few. It's not very common that these things are deployed yet because of the concerns about what they'll do and any damage they might cause. So this was a robot that we developed. It was to inspect an underground duct or a tunnel, and it ran along underneath a corridor. It was 150 meters long, and to help with the decommissioning, they needed to understand what materials were along this duct. And when we spoke to the people who ran the site, this is at Dounreay in the very north of Scotland, an old research facility. They said, well, they've spoken to people who operated the site in the past. They know that there's various materials that might be in that duct, but they really weren't sure what materials and the concentration of those materials. So we designed a robot for this. To design the robot, we first, there were manholes. So we lifted a manhole and we could put a camera down and we could get an understanding of what was below. So this is the tunnel. You can see it's got walls either side. It's about 2 meters wide, big pipe down the middle, and it looks nice and clear. Not much rubble in there. So we designed a track vehicle. This is the vehicle we designed. It's got a LiDAR on it. We asked them, what sensors do you want? And they just gave us all these different sensors that they thought would be useful. It was a daft question to ask. We had a beta sensor, X-ray, gamma, neutron. So this thing was just equipped with loads of sensors. It's got an arm on it, and that was so that we could take samples and swab samples as we went along. So this shows it being deployed. So the people deploying it, they're on kind of like the dirty side, the contaminated side. So they're all dressed in suits and we're on a nice clean side. We've got the joystick. It's completely teleoperated. Got lights and cameras. And it was probably, in terms of raw equipment, maybe 2,000 or 3,000 euros. So it's low cost because we're only going to use it once and then we're not going to get it back. So you can see there's a pair of gloves in the tunnel there. So it's trundling along. It's untethered, but we've got a fishing line just in case it got stuck. We could drag it back. So I was allowed to drive it. The proper researchers to just design it and develop it. I think this is me driving it, and we stop here because we're not sure how we're going to get over this rubble because there's more rubble than we thought. And the solution was you just drive it fast. So you go as quickly as you can, and you hope you don't ground. But so as it's going down, it's taking the sensor taking lots of measurements of gamma and X-rays. This is where we picked up this little puck, and you rub it against the floor, and you take a sample. That goes back on the robot. The robot goes back to the opening. The operators will pick it up, and they take that puck and they send that to the lab for an assay, and they determine what materials are on it. And when we tested that, we had every 10 meters we had a sample, and they found they had all sorts of materials, all the things, uranium, plutonium, all the things that they kind of expected to see, but much lower concentrations of them than they expected. So that was 2 weeks of deployment. It saved them €6 million from that 2 weeks. So there's huge benefits in deploying robots, and it prevented thousands of hours of people wearing suits and going into these environments. This is, I suppose, a next step. This is the wall of a nuclear reactor here. So this is where it's a research reactor in Slovenia, and this is the robot that we've designed. It's based on a jackal. It's got this is a gamma detector, and it's made of lead, and so it's like a pinhole camera. You point at it, and it will tell you if there's any gamma radiation coming from in a specific direction, rather than just from everywhere. So what we were able to do with that is we drove on the top left. That's the trail as it drove round this nuclear reactor, and the bottom left was when we take all those measurements, and we used Gaussian process regression to get a map of what the radiation levels were like in that facility. And that can be beneficial because it might be where the blue areas are. It might be people can walk through those areas. Where the red zones are, you want to avoid that. This on the right is our confidence in those measurements. So we take measurements, but if we don't have very many measurements, so on the top right here, we don't have very many measurements from there, so we're not that confident. So I probably wouldn't walk around that top right area unless I got the robot and did some more scanning around that area. This is probably my favorite robot. We had to design a robot that would get through 150mm access port. So nuclear industry has lots of nice big thick concrete walls, so you can't just take along big robots and stick them in. They can sometimes drill a hole. In this case, they had a hole. They told us it was 150mm. We designed the robot, and then they said, actually, it's about 140mm. So we had to redesign it. So this robot is designed, it's got these Meccano wheels, so it goes through the opening. It can go through, I think it says 120. I'm not sure if it's 120, 125mm. And it can also navigate through quite congested areas by reorientating itself. And I can find where my mouse is. And this is an image that it generates. So this is just a LiDAR scan. And so you can see there's a ladder there that's been left. You can see the vessels. So nobody's been in here for 20, 30 years. And so it just gives really an image of what it looks like. So when they're deciding how to decommission it, they know where things are and they know what it looks like. So the robot was able to get nice image from this side. It didn't go over this bridge, so it gets worse. You've just got a few points in a point cloud on there. And the nice thing about this robot, it creates lots of nice control challenges and optimization challenges. So here we want the robot to go from point A to point B, and by reorientating itself, it can start to move around, and you can have we have a model predictive controller which operates on the robot. It doesn't like certain orientations because it can flip over, and it doesn't really like being a long straight snake because it has very little maneuverability like that. So it's a really nice constrained optimization and control problem. And so here we've got an automatic optimizer on it, which is feeding set points down to the a model predictive controller, so it can move around this environment and it can avoid obstacles in there. And it does move in a pretty weird way at times. But yeah, nice piece of work. I'll be very quick with this. This was work done in Australia. 2 simulated bits of radiation, and what we did here is we're using a ClearPath Husky. We did this in partnership with CSIRO in Australia. And we just move around this location. I think one of these is maybe a video, maybe not. But it goes around the area and it's trying to explore. And what we want to do as we're exploring that areas, we want to avoid those radioactive areas, but we don't always know where they are. So as it's exploring, it will identify some areas and it marks them in red where there's radiation, and then it will try to avoid those radiation areas in future. So it just gives them, when you look at the trails, it won't go through those areas again. And we'll come back to that because that's the problem that you get with radiation damage to the robot. And I think Yael said before about levels of autonomy. A lot of the robots that we use are teleoperated because it's easier. This is a fully autonomous robot. It operates a bit like a Roomba vacuum cleaner. You drop it down, so you could drop it down on the floor in here. And what it's doing is it's scanning the area. It's moving up and down the area looking for alpha contamination. So it's a job that a human would typically do. And if you wanted to scan this area, you'd have a little wand in your hand and you'd have to bend down and you'd have to, it's alpha, so you can only detect it from a few centimeters. So you've got to sweep along the floor throughout this whole floor space area, and it would take you hours, get probably a very sore back. And what we do is put alpha detectors in the front of the robot, and then it just moves around, and over a few hours you just drop it down and it avoids all the obstacles and generates a map to show you where any radiation is. And then one of the problems is that if it finds radiation and it just drives through it, that contamination can stick to its wheels, and then it just moves it around the environment, which is what you don't want. So what it does is it hovers over the radiation, and then it will avoid that radiation. It will go around the radiation. So you make sure that it doesn't spread the contamination. So this causes lots of issues in the nuclear industry, because you then have a fully autonomous robot with some intelligence on it, and sometimes that intelligence is a black box. In this case, it is a series of if-then rules, so we can explain what it's doing, but it still creates some challenges for getting acceptance of the technology. Submersible robots. So this is one being deployed. You can see the person deploying it is all suited up. This is a submersible robot that we developed for inspecting these big storage silos. So they've got radioactive materials in there, and it can go in just with, typically you just want cameras. You want to have a look inside and see what's actually in there. And we did some work with this in Japan. This is some fuel debris, a simulated fuel debris. This is our robot, and the Japanese collaborators, they developed a sonar system, so it was mapping the where the obstacles were at the base of the reactor. So it's trying to understand what materials were in the reactor and where those materials were. And this is a floating platform or a boat. So again, it's for those, at the start I showed you these big swimming pools that they have, and you have lots of storage facilities for nuclear materials. And this robot, which we've designed, it's very similar to a wheeled vehicle. Rather than wheels, it's just got thrusters, but it moves in a omnidirectional way. And it would just, in this case, it's just going up and down the pond. This was developed for the the International Atomic Energy Agency, and they want to be able to go into nuclear fuel storage ponds, and they can see the fuel, blocks of fuel at the base of these storage ponds, but they don't know if those containers still contain the fuel, or some countries might have taken the fuel out and they may have put it into a separate nuclear program. And so they wanted this to be used to try and detect it. There's a fuel assembly there, and this could confirm that actually there really is the fuel inside that assembly. So it's just another inspection tool. But what we're now using it for is a specific problem we have is that when we're using underwater robots, we want to know their position. Underwater positioning is really, really difficult. In a room like this, we can set up cameras, and there's lots of SLAM techniques which you can use, and positioning is pretty straightforward now in indoor areas. Outdoor, you can use GPS. Underwater, it's really complicated. And so what we're doing now is we have our surface vehicle here, and we have a submersible vehicle. And you can see on the top of the submersible vehicle, we've just got a QR code. It's an April tag. So the surface vehicle, that knows where it is. In the nuclear industry, the ponds have nice big walls. So we put a LiDAR onto this, and it knows exactly where it is. It can then look down and it can see the April tag marker, so it knows where the submersible is. And it's quite complicated because the surface vehicle sways around a bit, so you have to take into account that sway, but then you can position the underwater robot to within a few centimeters. And what you have here is what we need to do is the surface vehicle has to track the submersible vehicle, so it can still see. It has to be able to see what it's looking at over fairly long, you know, up to maybe 100 meters. You can see that we've just dragged the submersible, and unfortunately, because this is fairly dumb, it's just moving up and down, expecting to track it, it's now lost sight of it, so it doesn't know where it is. What we've then done is we have a control system, and it uses the principle of having a virtual tether. So as one moves, they kind of move in unison and they track each other around the pond. And what we can then do is, because we're tracking this submersible vehicle from the top, looks a bit confusing, this photo here, but it's just showing multiple locations of the surface vehicle and the submersible vehicle, and we can start to track it. So the blue is the actual position of it, and the yellow and orange are the positions that we estimate using two different techniques. And we get within about seven centimeters. So it's pretty accurate. And that means that we can send submersible down. We can actually have it completely untethered. So we can send video feed backwards and back to a base station. We do that with Li-Fi units, so blue flashing light, and then it knows its position, so you can have fully autonomous, untethered submersible vehicles going around these ponds. So that's kind of the inspection robots, the mobile inspection robots. The other area we're working in is trying to look at manipulation, how we manipulate nuclear materials. This is, you can see in the background, this is a glove box, and we want to try to use robots in these glove boxes rather than people. And if I switch now, you'll see that this is the digital twin. So you'll see that the quality now of the digital twins you get. Sometimes I see the videos, and you think it's a real system, and actually it's the virtual system. That the quality is that good now. And so here, this demonstrates this person is moving this joystick to operate a manipulator that's inside the glove box. It's a Kinova manipulator which can go through the glove port, and it works in parallel with a digital twin. And in a digital twin, you can put obstacles in there, virtual obstacles, so you can have regions where the operator can't go into. So if you had a sensitive area within that glove box, you can partition that off, and the operator himself doesn't have to worry about whether or not they stray into that area. You have an autonomous system which is preventing them moving into those areas. So the intention with this is that you would perform operations in the glove box autonomously, without humans having to put their hands in. And then we're doing a bunch of work on top of this to provide some autonomy. So this is some operations where we're trying to automatically grasp an object. So rather than the operator carefully working out, these are really difficult to, there's lots of manipulators around here, and you can see it's difficult to operate them. So you just point at something and say, can you go and pick that up? And so we're doing the autonomy there. And this here is trying to develop different ways in which to operate the manipulators. They're difficult with these joysticks. So here we've got a real sense camera, and as the person here is moving their hands, the real manipulator is moving in sympathy. This one is developing control systems. This one and the final one here, it's developing control systems so that the operator isn't having to worry about whether they collide with objects that they shouldn't. You've got all sorts of joints, so you don't want the joints bashing into things. So you've got control systems which work out these areas, and then all the operator needs to do here is it's positioning the end effector, and then the rest of the robot won't hit anything. I will skip through these with time, but radiation tolerance. If you take a robot into a high gamma area, then the gamma radiation will destroy the electronics. Anything that's silicon, it has a limiting effect. They're more tolerant than people. We'll survive. Well, we will die at about 4 or 5 grays, and a gray is a measurement that they use for radiation. So we'll die after 4 or 5 grays. Your phone might last maybe 50 grays. I probably wouldn't want to put your mobile phone in, but it's more tolerant than we are. And you come to a lot of damage before you got to 4 or 5 grays. But here we're trying to develop this robot so that we've removed we've removed all the silicon really from this robot, so that it can operate in these highly radioactive environments. The video doesn't show you a lot, except the robot can move. So it's a radiation tolerant robot. It will go into some of these very high radiation dose environments, and we know now that it can move. We can put a camera on that and we can get video footage. And this is where we test it. So this is a big lead line vessel. It's got a cobalt-60 radiation source in the base. You close the door, the cobalt-60 goes up at the back, and this is our an upboard, a microprocessor, and we test it, the effect of radiation, and whether or not it damages it, and it will destroy it, and you can't use it again. So so we can now develop things that are highly tolerant. I am conscious of time, so I'll zip through some of these. So this is expanding outside of nuclear, but it's a nice application. This is a drone, and it's being deployed through 150 millimeter access port into a mine. And the actual scenario here is that we have lots of railway lines in the UK, and some of them are built on old mines, and often they need to inspect the mine to make sure that it's not all going to fall in. And so this is a drone going in, and it's all folded up, so it's been designed so that the drone can fit through 150 millimeter hole. This is it being deployed. So this is now inside the mine, and if you watch, what you'll see now is that there's a little motor whirring away, and you can see the arms start to rise up. We had a brilliant design engineer who designed a lot of the mechanics in this. So once the drone has unfolded itself, then the rotors will start, and it releases from its connection points at the top soon, and then it will fly inside. So it can fly inside. It can take measurements and scans inside, and when it's finished, it will return and it will fly back to its original position. It will fold down the rotors, and it will be lifted out. So this is it moving around inside, and then eventually it comes back to where it came in, connects itself back up, unfolds, and then or folds itself up, and then it will pop out the top again. So lots of really nice applications wherever you need a small access port. This was a robot that's designed for inspection of these enormous wind turbines, offshore wind turbines. At the moment, you have people who go out on boats to inspect these wind turbines. And this is a drone which takes this, it's called a blade bug. So you can see it's got a little ring here. The drone will come down and it picks it up, takes it off the wing after it's done its inspection. It's a really clever mechanical device, and I think it was the bit that took the most time was trying to make sure that it could pick it up and release it. So it would drop it off first onto the wing of the wind turbine, and then soon enough it picks it up and takes it away from the wind turbine. It grasps it, and then it whizzes it away. And the intention is that you don't need people going offshore because it's a really nasty environment. That's the robots. This is our new facility. It looks lovely. We're right by the sea. This is it's in the Lake District, the most beautiful part of the Lake District, most beautiful part of the UK, I would say. This is our shed. It looks awful from the outside. It's a collaborative facility. University of Manchester, the academic lead in it, and we work with organisations from the nuclear industry, Sellafield and other organisations. This is what it looks like inside. Lots of robots, lots of equipment, lots of test facilities, and it's open for anybody to come and use. If you want to work with the nuclear industry, if you've got researchers who want to work with the nuclear industry, or you just want to come along and learn a little bit more, we've got space. People can come out and use the facilities we've got. Lots of robots. This is the latest robot, which arrived on Monday, which is a unitary humanoid robot. I don't think it's got a lot of use in the nuclear industry just yet. I think it will fall over. We've got Spot robot is being used. That is being taken onto the Sellafield site regularly now. There's very few situations where you want 2 legs rather than 4. 4 legs seems much better for most of these applications than 2 legs. But you're welcome if you want to use any of these robots. Come over and you book them out, and you can use them. I'll skip that one. And finally, these are the funders. So we've been very fortunate. We've got a lot of support from Royal Academy of Engineering and EPSRC, which is the UK Research Council, and they funded a bunch of these different programs. And we also have some really good support from Nuclear Decommissioning Authority, UK Atomic Energy Authority, and Sellafield Limited, who we support a bunch of the work. So that's it. If you want to get more involved, then please just let me know. You're welcome to come over, use facilities. There's no charge if you want to use them. So that's it, and thank you for your time.
So thank you, Barry, for this very interesting presentation. And if there are questions.
Hi, I was wondering what is sort of the timeline from this idea of making a specific robot and then till the moment it's like in a plant, or like, because yeah, we now see like lots of research probably summarized in like in half an hour, but yeah, I was wondering about that, because then you use it and then what? Because often with EU project, etc., you have a prototype and then it's done, but I assume that when it's successful that they want to make multiple copies of it so you can use it multiple times.
Yeah, so there's lots of different answers. The nice thing about it is that the decommissioning of that whole site, that Sellafield site, the plan is it will take 120 years. So you can start developing things now and then use them in 50 years' time. So for researchers, it's fantastic. But actually, they also have some immediate problems, and we work with them. We develop robots maybe over a period. The robot that went into that tunnel, that was development took about 18 months. It was delayed because of COVID. It was deployed, and that was an 18-month period from start to finish. The robot that was like the Rumba robot that just goes around scanning for radioactivity, we started that in, I think, 2017, 2018. We took it on site, we demonstrated that it worked. And now we're supporting the development of a commercial system, and it just takes so much time. It takes time to get the robot onto site. There's so many restrictions about getting things on site. And yeah, you're right. They want a commercial product. They want to work with that commercial product to get it perfect, and then they'll want multiple copies of it. At that point, they'll probably say we want them tomorrow. So I suppose in answer, different things have different timelines. So a lot of the inspection, they want to know what's happening inside buildings. Some of these buildings are just shut up. People haven't been in for 10, 20, 30 years. They just want cameras to go in, see what's in there. Some of the manipulation, that's longer term. So they're looking at maybe things in 5 to 10 years. So there's timelines for everything, all different.
When you use those robots in the nuclear environment, then afterwards they are contaminated themselves. So I didn't hear you talk about how to handle that.
No. So if the robot that we deployed at Dounreay that went in the tunnel at Dounreay, if you go to Dounreay, you can see it. It's in a plastic bag and it sits on the side. So it's not broken, but we can't take it back to the lab because the some of the problems that plutonium powder, it's very, very fine, and it's like a very fine dust, so it will get into all the crevices. So you can never take those robots back into.
So do you also envision a kind of decommission process for the robots that were used in decommissioning the nuclear sites?
They will be smashed up and treated as waste. But what we can do is we can try to reuse them. So at the moment, they have certain restrictions. They don't like to. I suppose the Ghostbusters term, we cross the streams. They don't want to take a robot that's been in one facility and take it to another facility because that can contaminate the other facility. But in my view, they're both pretty horrible in-hospital environments. It really probably doesn't matter. So what we should be looking at is how can we take this robot? It's now in a bag, but it works. We can pick that up and we can carry it across to another facility and we can deploy it again. So I think it's really important that we do start to reuse these robots and understand how we can better reuse them. Some people have looked at they kind of put a shield over the entire robot so it can be cleaned, but that just seems very impractical. I don't think that's the solution. I think the solution is you make the robot so that it can be moved from one facility to another. And the spot robots have been used in multiple facilities, and what they do is they put a plastic suit over the
like human,
like a human. So you put a suit over it, and then you take the suit off, and then you can take that robot away, and you will have to scan the robot, but in theory it shouldn't have problems. And special suits have been designed for spot.
Okay, nice.
Thank you for your nice presentation. I have a question about that kind of a snake robot, and it is what was the biggest what was the biggest control challenge with that complicated robot?
So there were some really interesting control challenges. One of them is just understanding the controllability of it. Some orientations, it's really, so when it's in a U shape, it's really good. It can move around and it's great. But you want to restrict it being in a long shape because it falls over because of the mass. We never thought to position the mass and how we position the mass inside the robot. So there are certain orientations that it doesn't operate very well in. So it's designing a control system that took that into account. The other thing, which I don't think it's on those videos, but the center of mass, when it's in the U shape, the center of mass, it should be in the center, but actually it's in the back, in the kind of base of the U part. And what that means is it lifts the wheels up a little bit, so actually it doesn't move very well. So what we had to do is we got pieces of lead and we stuck those to the end pieces, and then it moved around a lot easier. Our first version was in plastic and it didn't happen, and we just didn't really think when you make it out of metal it's a lot heavier, and so that was one of the control challenges that we had. But actually I think you could have PhD students working for years and years on all the different control challenges in that, and the optimization, how you get it to move around areas. It's a fascinating problem.
Thanks for your presentation again. We saw many theater vehicles, but what about the challenges of powering these vehicles when you want to work fully out in autonomous mode and you want to charge them again and you want to do a battery swap, or you want to do whichever technique you use? How can you make them more sustainable for reusage and also for the energy management, for instance, of the snake, that they have to consume a lot of power doing these movements now?
So yeah, and so it's really important, particularly if what we really want to do is to have robots that will be in a facility permanently, and every morning they will. So if some of the storage facilities will be a room much like this, a lot taller, and you'll have lots of canisters, lots of containers in there, and you want a robot to wake up first thing in the morning and to go through and check, is there any new corrosion on any of these containers? Hydrogen can be produced, so the containers can start to expand a little bit, and you need to recognize that, and that's daily surveillance. And I think the way to do that is to adopt the approach that the Rumba vacuum cleaners use. It goes back to a base station and recharges. We've looked at, can you recharge through thick concrete walls? It's not my area of research, but it's feasible that you can do that. So you can recharge these robots through walls. We've looked at hot swapping batteries. So drones are used more and more frequently now. They can only operate for maybe 10, 15 minutes, although they do use some of the ones where the drone is has a permanent tether. But we've looked at hot swapping the batteries, and we've demonstrated that's feasible. So you can build a system where you hot swap the batteries. We can build. It's been called like an aircraft carrier that the Spot robot wouldn't walk around, and it has a drone on its back with a charging mat, and so the drone takes off, flies around, comes back on a charging mat, and you can. So whilst you can't take the robots out, often you can't take them out of the facility. If you make something that's very modular, so the robot that we deployed in the tunnel, we made it really simple. We had some tape, and you could pull the battery out and push another battery in. And the operators could do that when they're all suited. And you have to think about what they can do when they've got thick gloves on. So they can't change a normal battery because they'll need a little screwdriver, but you just design them so that you can take things apart easy when you've got gloves on. So it's a real problem. But there are some simple solutions and maybe some more complicated solutions that we need to be looking at.
Yeah, thank you very much. That's really interesting. Quick question on you explained about the different challenges that we can have in a nuclear setting, right? And it's obviously very diverse, a bit of everything, underwater, on land, in the air, etc. And on the problem part, there are some common elements, right? It's always radioactive, as you mentioned. Operators have gloves on, etc. So it's quite clear what is the common thread you can find on your constraint space. But is there any common thread on your solution space? You showed all these different robots. Is there any scalability there? Any lessons learned that can be applied from one to the other? Any software element or?
There are. So I think you have to consider that the nuclear industry is new to robots. Well, actually, that's not quite true. They've used remote operations for many years because when you've been decommissioning, people have been decommissioning reactors for 50 years, and often it's been done remotely. So they have experience with using big manipulators and operating them remotely. What we're seeing now is much more state of the art and some progress on the robotic systems themselves. But you're right, what you can't have is one robot for this, one robot for another, one robot for another deployment. The Spot robot, they are getting a lot of use out of the Spot robot because it's so versatile. So it can walk around a room like this without you worrying about it. If there's rubble on the floor, it can still walk around a room. Whereas some of the wheel vehicles that we've got, you think, well, it could go around this room, but if there's a big pile of rubble, then it's stuck. It can go up and down steps. So that's made a big difference. I think I see a lot of the times when the Spot robot's being deployed, I think there's cheaper and simpler solutions than Spot. Just get a Husky or a cheaper robot and send that in. But actually, I think it's quite sensible. They've got a robot that hundreds of people can now use, and it can solve lots of their different problems. So that's a good example of a robot that can solve multiple problems. It's got the manipulator as well, so it can start to do things. But it's not going to solve everything, and you will need other types of robot. And I think that's what one of the things we're looking at is how can we then start to use multiple quadruped robots, because a single quadruped might be able to lift 5 kilos, 10 kilos, but maybe with two, you can one can grab hold of a pipe, another can come along and cut it, and then you can take that away. So multiple robots, perhaps using quadrupeds. I don't think quadrupeds are the solution to everything, but I think they are helpful in some of these environments. But you're right, you've got to have some commonalities between the robots that you're using.
Yeah, sorry, I'm monopolizing a little bit. But another question that is maybe a little bit outside of your of what you discussed, but on the new generation of nuclear power plants, right? So small modular reactors, etc. They talk a lot about having the system being walk-away safe, and the fact that it's going to be much cheaper because you don't need anybody on site, right? So essentially, they see the nuclear power plant as a robot, right? Fully automated, doing operations autonomously as a robot.
Yeah.
Is that something we should believe in, or not?
Well, it is outside my area. I'm not a nuclear engineer, but however they're operating those plants, they will need to be monitored, and so I think that's where the robots come in. And we've been involved in quite a few discussions about how you might just monitor the perimeter. And do you really want just people walking around the perimeter? Why not have drones going around the perimeter? Why not have well, you can design these places better. The problem that we have at Chernobyl, Fukushima, and Sellafield is they've never been designed for robots. So if they are going to have these fully automated, then they need to put a lot of effort into making sure that they are you can navigate around them in a robot, and they are designed for the use of robots, and that would provide a lot of help. Whether or not they then use that they can run without people, I don't know.
Thanks a lot. Do you have some more to say about the material limitations for the robots to be used in nuclear reactors, especially the ones that you use for underwater applications? Are they different than regular ocean investigation robotic materials that you can use?
It's a really good question. So the electronics of a robot are damaged by gamma radiation, but also the materials are damaged as well. So when when that robot that looks quite basic, it is very basic. That is radiation tolerant, we have to consider not just the electronics. You've got to consider everything about the design. So if you have any PVCs, polyvinyl chlorides, what happens with them is that they will produce hydrochloric acid or hydrofluoric acid in gamma environments. So that's an acid, and it will cause lots of problems. So where you've got wires and cabling, you need to make sure that you don't have PVCs in the polymers that coat the wires. In the motors, a lot of motors have PTFE tape. I don't know if that, yeah, and that's affected, so that will disintegrate very, very quickly. So we have to look at, when we've been designing that robot, we could only use particular motors because we would contact the manufacturer and say, can you tell us exactly what's in your motor? And some of them would say, either we don't know or we can't tell you. And some would say, yes, here's all the information. So yes, we have to be careful. I think the aquatic robots, not so much, because you do have the shielding from the water. So the radiation dose isn't going to be as high as in some of these other environments. And some of these storage facilities, the pH is kept at about 11. So it's quite caustic. That will cause some problems. So we do need to take that into account. But it's not seawater, it's fresh water. But you have to consider the environment when you're choosing the materials. But I don't think it's any harsher than seawater, except when the pH is 11. Well, the silicon, there'd be concerns about it. That's just with the amount of gamma radiation. So I suspect that in underwater conditions, it's probably not a significant problem. But if you're underwater and you're going to be there for a long time, then maybe it does become a problem. You just have to look at it, because the problem with the damage to electronics, it's cumulative. So if you're at a very low dose rate for a very long time, that has the same effect as if you're very high dose rate for a short time. So it depends a little bit about longevity.
So let's thank again Professor Lennox for his talk. And I give the occasion to remember that all our fellows are here, so we will have time for interesting discussions.